We'll conclude this lesson by looking at two theorems from AP Calculus that are very much linked. In fact, one is a generalization of the other. And these really are central to much of what makes calculus work. The first is called Rolle's theorem. Recall Rolle's theorem says this. It says let f be continuous on a closed interval, differentiable on the open interval of those same points, and also that f of a is equal to f of b. This means that you could translate these down so that they're both equal to 0, but it's more generally they just need to be, the endpoints need to be the same, have the same output. With this, the theorem then says, there must exist some c in the open interval. There's some c in the middle, such that the derivative at c is equal to 0. As a picture, it looks something like this. Suppose you have some function, and it's on some interval a to b, and all I know is that f of a is equal to f of b. So I know I have some function where the endpoints are at the same height. Maybe they're 0, maybe they're some other non-zero number, but they're the same, whatever they are. Function says, then since this is continuous and the derivatives exist everywhere, that no matter how I draw this function, that there's got to be at least one value of c where the derivative is 0. In this particular function, there happens to be two values of c, but there's got to be at least one. Intuitively, I hope it makes sense that this theorem should be true. And we're going to, what I'd like to do is use some of the definitions we've already stated to explain why this more rigorously must be true. So we're going to let f of x satisfy, just to save some writing here, satisfy the hypothesis. Meaning, whatever this function is, it's continuous on the closed interval and differentiable on the open interval. What is this? What do these things mean? Well, we saw that since this function is continuous on this closed interval, that it must be bounded. Meaning it does not blow up to infinity. What does bounded mean? Bounded means that there's got to be some biggest or smallest value that this function ever achieves. It's stuck between, at minimum, it's stuck between two numbers. We'll pick what is that biggest or that smallest value that the function could ever be. This means that there must be either a max or a min, or maybe both, somewhere on the closed interval. Might be one or the other, it could be both, but there's at least one of them. So wherever this max or min is, we're going to let c be that value. So let c be the input that achieves this maximum or minimum. This max or min. And since the function is differentiable, this means that the derivative has to exist at c. The derivative exists at this extrema. And what is the derivative of a max or min? A derivative of maximum min is a horizontal line. Therefore, the derivative at this max or min is got to be 0 because it's an extrema. A generalized version of this theorem says that it's called the mean value theorem, which again you may have stated in calc and you solved some problems involving the mean value theorem, and that's great. The concept of what this theorem is and how it's used underlies everything that goes on in the rest of calculus. It's so fundamental to the logical consistency of the subject that it's definitely worth our time to not only make sure we remember what the theorem states, but I think the understanding of why the theorem works is also crucial. So I'm going to state the mean value theorem and then draw a picture of kind of what it's trying to say. And then we'll think about how, and we'll state incredibly, I think, clever and beautiful mathematical proof of why this thing actually works. So the mean value theorem states the following. It says let f be continuous, just like Rolle's theorem, on a closed interval and differentiable on an open interval. We'll say on the open interval AB. Then there must exist some C in the open interval such that the following is true. That the derivative at this value C is equal to the following expression: f of B minus f of A over B minus A. So note, what is this? This is saying the derivative is equal to this kind of crazy formula, but this formula should look very familiar. This is, in fact, y2 minus y1 over x2 minus x1. This is the slope formula. So what it's really saying is that, or what this is trying to put into symbols, is that there's got to be, if this function is continuous and differentiable on some interval, then there's got to be some point in the middle such that the instantaneous rate of change is equal to the average rate of change, which is why this is called the mean value theorem. As a picture, it might look something like this. So again, I'll just draw in the first quadrant, but it doesn't really matter. Here's A, say here's B. And this function has some output, f of A, and some other output, maybe it's up here. And unlike Rolle's theorem, these do not have to be at the same, have to be equal to each other. But saying that if this function is, since this function is continuous, that there's got to be some point in the middle such that if you calculate the average rate of change, which would be the slope of the line created by connecting A to B, and then it's got to be at least one, if not more, value somewhere in the middle such that the average rate of change, or the slope of the tangent line, is exactly parallel or equal to the slope of this average rate of change. So there's got to be some C such that the derivative at this value C is equal to this average rate of change. In my picture here, it looks like there's probably another one. It looks like there's another one like over here somewhere as well, where these all are parallel. This is a sort of picture that you're going to be asked to draw, definitely asked to draw on the IB exam, and it's the sort of thing that shows up in the AP Calculus exam as well. This understanding of what the mean value theorem is trying to state. I think the proof of why this is true is incredibly. It's one of the really beautiful things in math, or at least this particular proof. It's very surprising. I think that's one of the reasons why I think it's beautiful, and it really relies on just knowing some pre-calculus, some knowing how to transform and how to build a very clever formula, or a very clever function off of out of some transformations we know. So the proof looks something like this. Let's consider A following function that's built from this function f, this more general function f that we're trying to understand. And again, I don't know anything about what the graph of f looks like. All I know is that f is some continuous function, and it also has derivatives everywhere in the middle. So I'm going to build this new function. I'm going to call it h. And this function is the following. It starts as our original function, but then I'm going to transform this. And I'm going to transform it in the following way. I'm going to subtract the following term. I'm going to subtract the average slope times x minus the initial value. And then I'm also going to vertically shift this down by whatever the initial value of the function is. This function is continuous itself. It's differentiable itself because f is continuous and differentiable. This is really just a number times a line, and lines are continuous and differentiable, and this is just a constant. So this is also continuous, differentiable, so on and so forth. However, this function has some really cool properties. So again, we'll state that since f is continuous and differentiable on this open interval, then h is as well. Then this new function we just made up is as well, for those following reasons. Also, h has this incredibly cool property. If you look at h at the initial value of a of this interval, we get the following. You get h would be equal to, when I plug in a everywhere for x, so that's f of a minus f of b minus f of a over b minus a times a minus f of a. This middle term, a minus a is 0, so this middle term is 0, which means you're left with f of a minus f of a, 0. So this new function h is actually dead equal to 0 at the first endpoint. Similarly, let's look at what its value is at the second endpoint. That would be f of b minus f of b minus f of a over b minus a times now b minus a minus f of a. At the other endpoint, let's see, the b minus a or b minus a, those cancel. Do that in orange. Those cancel. So you're left with f of b minus f of b minus f of a minus f of a. This is, if I distribute this minus sign, this is f of b minus f of b plus f of a minus f of a, which is also 0. What does this mean? This means that the value of the function's outputs are equal at the endpoints, which means this function satisfies Rolle's theorem. So h of x satisfies Rolle's theorem, meaning that there exists some c in the open interval such that the derivative of h at this interval, at this value, c, is equal to 0. What is the derivative of h? Well, it's the derivative of this function. What is the derivative of this function? Well, we do part by part. Derivative of f of x is f prime. I'll plug in c. The derivative of this term, well, this is a constant times a linear function. So the derivative of x minus a is just 1. So this is the same as minus f of b minus f of a over b minus a. Minus f of a, well, this is a constant. So the derivative of constant is 0. So the derivative of h is 0, but it's also equal to this expression. So rearranging, this tells us that the derivative of f at c is equal to f of b minus f of a over b minus a. Again, an incredible result. It's incredibly clever to come up to do something like this, and I think this is one of the really truly beautiful things that you encounter in mathematics.